Now, following the formation of the neutron star, what happens is the supernova. The supernova is a sudden release of gravitational binding energy that generates a shock wave. This blast wave, propagating through the atmosphere of the star, triggers a series of explosive nuclear reactions along its path. This violently heats up the atmosphere of the star, accelerates the stellar envelope, and ejects about 10 to the 53 erg of energy. In a few hours, the shock wave reaches the surface, and from the outside, the star is seen to explode. So let's see what actually is happening. What exactly is happening to the ejection of the supernova? Where is this energy coming from, this 10 to the 53 erg of energy? So let's dial it a bit back to the formation of the neutron star. You have the collapse of the core. As I said, when the support of the generate pressure of the electrons in the core is gone, the core collapses in free fall. And the collapse is going to continue until nuclear densities, which is a density of about 10 to the 14 grams per cubic centimeter, when neutron degeneracy pressure kicks in and halts the collapse. In the end, then, you pass from something from the core of iron, which is the white dwarf, about the size of the Earth, to something that is much, much, much smaller, about 10 kilometers. That's the size of a neutron star. It takes about a second for this to happen. The collapse speed is like a fraction, a fourth of the speed of light. What's going on here is that this collapse releases a lot of gravitational potential binding energy. As we saw, in the 19th century, it was thought that the sun shrinking its radius was what would generate the luminosity. And even though that's not what is actually powering the sun, I hinted that there are other systems where the release of gravitational binding energy is the source of energy. This is one of these cases. The associated release of gravitational potential energy here is what is powering the supernova. The releasing gravitational potential energy, we calculated previously the total amount of gravitational binding energy. That's gm squared over the radius. And when an object contracts, there is an associated release in gravitational binding energy, which is half of the potential energy. Now, we can assume that since the radius of the remnant is much, much smaller than what it started with initially, that the energy liberated is half of the total gravitational binding energy. So it's 3/10 of gm squared over the radius. Now, plug in some numbers here. Say that the mass is about 2 solar masses. And the radius then that it starts is about 10,000 kilometers, the radius of a white dwarf. What you get then, if you plug in these numbers, is that the energy is about 10 to the 53 erg. So that matches the energy that we expect from a supernova. This is the energy of a supernova. The implication is that supernovae are powered by the energy released when the iron core collapses into a neutron star. Now, the precise mechanism of the explosion is not well known, but its thought is that the sudden release of gravitational energy generates a blast wave that triggers explosive nuclear reactions along its path. The shock violently heats and accelerates the stellar envelope. In a few hours, the shock wave reaches the surface, and from the outside, the star is seen to explode. The supernova 1987 was the first opportunity to study a supernova with modern instrumentation. And indeed, the progenitor was found to have a mass of 20 solar masses, and neutrinos were detected 4 hours before the optical event. And indeed, the burst of neutrinos is precisely what you expect from a supernova explosion. Let's understand why. The energy of a supernova is 10 to the 53 ergs divided into 1%, so about 10 to the 51 erg in kinetic energy, the shell expanding through the interstellar medium. 0.01%, so 10 to the 49 erg, that's photons. That's the luminosity that we see. The vast majority, 99% of the explosion, is released in neutrinos. What is going on here is that when the degeneracy is lifted and the beta decay is finally allowed again, then the neutrons decay again into protons, electrons, and neutrinos. But because the densities are still very high, the protons and the electrons are allowed to recombine into neutrons and neutrinos. And this reaction is now occurring in a loop. You have beta decay followed by inverse beta decay, looping. What you have here from this is a flood of neutrinos. Both reactions release neutrinos. The neutrinos escape, carrying the energy away. This cooling process is known as Urca process, and it cools the core of the supernova from about 10 to the 11 Kelvin, from 100 billion Kelvin to about a billion Kelvin, when the electron degeneracy kicks in again and inhibits the beta decay. Now, during this cooling, the energy of the gravitational collapse was converted into this 10 to the 53 erg worth of neutrinos, which is the main luminosity of the event. It is estimated that of the order of 1% of the energy of the neutrinos is deposited in the shock that leads to the kinetic energy of the explosion. So this blast wave here that is happening is the neutrinos are released, and then 1% of the energy of the neutrinos accelerates the envelope, and the rest of it, the 99%, escape. Now, this blast, because of the shock, is converted into photons. It heats up the gas and then through Bremsstrahlung, it generates the 0.01% of the luminosity that is seen. 1% of the kinetic energy is converted into photons, converted into radiation that then escapes and is observed as the luminosity of the explosion. So that is the pathway. You have the energy being converted into neutrinos. 1% of the energy of the neutrinos accelerates the envelope, and 1% of that kinetic energy, because of the high temperature of the shocks, is converted into luminosity by Bremsstrahlung radiation.